Hello everyone, my name is Sham Parekh. I'm a student of BSc Chemistry Honours first year. Today we are going to read the chapter acid and bases, and here we will be covering about the types of acid and bases which were proposed by different scientists like Arrhenius, Bronsted-Lowry, Lewis, Lux Flood, and we will also categorize acid and bases on the solvent system, and we will then read about the HSAB, that is hard soft acid base principle. So let us start. Acid and bases are important substances in health, industry and the environment. One of the most common characteristics of acid is their sour taste. Lemons and grapefruit taste sour because they contain acid such as citric acid and ascorbic acid, vitamin C. Vinegar tastes sour because it contains acetic acid. We produce lactic acid in our muscles when we exercise. Acid from bacteria turns milk sour in the production of yogurt and cottage cheese. We have hydrochloric acid in our stomach that helps us digest food. Sometimes we take antacids, which are bases such as sodium bicarbonate or milk of magnesia, to neutralize the effect of too much stomach acid. The term acid comes from the Latin word acidus, which means sour. We are familiar with the sour taste of vinegar and lemons and other common acids in food. In 1887, the Swedish chemist Svante Arrhenius was the first one to describe acids as substances that produce hydrogen gas ions H positive when they dissolve in water, because acids produce ions in water. They are also electrolytes. For example, hydrochloric acid dissociates in water to give hydrogen ions H positive and chloride ions Cl negative. The hydrogen ions give acids a sour taste, changes the blue litmus paper to red, and corrodes some metals. Naming acid. Acid dissolves in water to produce hydrogen ions along with a negative ion that may be a simple non-metal, anion or a polyatomic ion. When an acid dissolves in water to produce a hydrogen ion and a simple non-metal anion, the prefix hydro is used before the name of the non-metal and its IDE. Ending is changed to ic acid. For example, hydrogen chloride dissolves in water to form HCl, which is named hydrochloric acid. An exception is hydrogen cyanide, which as an acid is named hydrocyanic acid. When an acid contains oxygen, it dissolves in water to produce a hydrogen ion and oxygen containing polyatomic anion. The most common forms of an oxygen containing acid has named the end with ic acid. The name of its polyatomic anion ends in 8. If the acid contains a polyatomic ion with an IT ending, its name and in OS acid. The halogen in group 7A can form more than 2 oxygen containing acids. For chlorine, the common name is chloric acid, which contains the chlorate polyatomic ion. For the acid that contains one more oxygen atom than the common form, the prefix per is used. HClO4 is named perchloric acid. When the polyatomic ion in the acid has one oxygen less than the common form, the suffix os is used. Thus HClO2 is named chlorous acid. It contains the chloride ion. The prefix hypo used for the acid that has 2 oxygen atoms less than the common form. HClO is named hypochlorous acid. Bases. You may be familiar with some household bases such as antacid, drain openers, and oven cleaners. According to the Arrhenius theory, bases are ionic compounds that dissociate into cations and hydroxide ions, OH minus ions, when they dissolve in water. They are another example of strong electrolytes. For example, sodium hydroxide is an Arrhenius base that dissociates completely in water to give sodium ion Na positive and hydroxide ion OH negative. Most Arrhenius bases are found from group 1A to 1A and 2A metals such as NaOH, KOH, LiOH, and COH2. The hydroxide ions give Arrhenius bases common characteristics such as bitter taste and a slippery feel based on litmus indicator blue, and phenolphthalein indicate pink. Naming bases. Typical Arrhenius bases are named as hydroxide, like lithium hydroxide LiOH, sodium hydroxide NaOH, potassium hydroxide KOH, COH2 calcium hydroxide, AlOH3 aluminum hydroxide. So these were the names. Now we will discuss about the Bronsted-Lowry concept. In 1923, J. N. Bronsted in Denmark and T. M. Lowry in Great Britain explained the definition of acid and bases to include bases that do not contain OH minus ions. A Bronsted-Lowry acid can donate a hydrogen ion H positive, and a Bronsted-Lowry base can accept a hydrogen ion. A Bronsted-Lowry acid is a substance that donates H positive. A Bronsted-Lowry base is a substance that accepts H positive. A free hydrogen ion does not actually exist in water. Its attraction to polar water molecule is so strong that the H positive bond to water molecule and forms a hydronium ion H3O positive. Like water plus hydrogen ion, it forms hydronium ion. We can add the formation of a hydrochloric acid solution as a transfer of H positive from hydrogen chloride to water by accepting an H positive in the reaction. Water is acting as a base according to the Bronsted-Lowry concept. In another reaction, ammonia NH3 acts as a base by accepting H positive when it reacts with water, because the nitrogen atom of NH3 has a stronger attraction for H positive than oxygen. Water acts as an acid by donating H positive. NH3 plus H2O, it gives NH4 positive plus OH negative. So here NH3 acts as a base as it has accepted H positive ion, and H2O is an acid as it has donated H positive ion. Now we will read about the conjugate acid base pair. According to Bronsted-Lowry theory, conjugate acid base pair consists of molecules or ion related by the loss of one H positive by an acid and the gain of one H positive by a base. Every acid base reactions contain two conjugate acid base pair because an H positive is transferred in both the forward and reverse direction. When an acid such as HF loses one H positive, the conjugate base F minus is formed. When the base H2O gains one H positive, its conjugate acid H3 positive is formed. Because the overall reaction of HF is reversible, the conjugate acid H3 positive we can donate H positive to the conjugate base and reform the acid HF and base H2O. Using the relationship of loss and gain of one H positive, we can identify the conjugate acid base pairs of HF by F minus along with H3O positive by H2O. In another reaction, ammonia NH3 accepts H positive from H2O to form an conjugate acid NH4 positive and conjugate base OH minus. Each of these conjugate acid base pairs NH4 positive by NH3 and H2O by OH minus is related by the loss and gain of one H positive. In these two examples, we see that water can act as an acid when it donates H positive or as a base when it accepts H positive. Substances that can act as both acid and bases are amphoteric or amphiprotic. For example, water, the most common amphoteric substance. That acidic or basic behavior depends on the other reactant. Water donates H positive when it reacts with stronger base, and it accepts H positive when it reacts with stronger acid. Another example of an amphoteric substance is bicarbonate HCO3 minus with a base. HCO3 minus acts as an acid and donates one H positive to give CO3 2 negative. However, when HCO3 minus reacts with an acid, it acts as a base and accepts one H positive to form H2CO3. Now we will discuss about strength of acid and bases. In the process called dissociation, an acid or a base separates into ions in water. The strength of an acid is determined by the moles of H3O positive that are produced for each mole of acid that dissociates. The strength of a base is determined by the moles of OH minus that are produced for each mole of base that dissolves. Strong acids and strong bases dissociate completely in water, whereas weak acid and weak base dissociates only slightly, leaving most of the initial acid and bases undissociated. Strong and weak acids. Strong acids are example of strong electrolytes because they donate H positive so easily that the dissociation in water is essentially complete. For example, when HCl is a strong acid dissociates in water, H positive is transferred to H2O. The resulting solution contains essentially only the ions H3 positive and Cl negative. If we consider the reaction of HCl in H2O as going 100% to products, thus 1 mole of a strong acid dissociates in water to yield 1 mole of H3 positive and 1 mole of its conjugate base. We write the equation for a strong acid such as HCl with a single arrow. HCl gas plus H2O liquid, it gives us H3O positive aqueous plus Cl negative in aqueous. There are only 6 common strong acids which are stronger acids than H3O positive. All other acids are weak. So here are some relative strength of acids and bases. Hydrochloric acid, hydroboric acid, perchloric acid, hydrochloric acid, sulfuric acid, nitric acid, hydronium acid. So the topmost is the most strongest acid and the bottommost, for example water, is the lowest acid, is the weakest acid. Acids are weak electrolytes because they dissociate slightly into water, forming only a small amount of H3O positive. A weak acid has a strong conjugate base, which is why the reverse reaction is more prevalent. Even at high concentration, weak acids produce low concentration of H3O positive ions. Many of the products we use at home contain weak acid. Citric acid is a weak acid found in fruits and fruit juices such as lemon, oranges and grapefruits. The vinegars used in salad dressing is typically a 5% mass by volume acetic acid solution in water. A few HC2H3O2 molecule donate H positive to H2O to form H3O positive ions and acetate ions C2H3O2. The reverse reaction also takes place, which converts the H3O positive ion and acetate ions back to reactants. The formation of hydronium ions from vinegar is the reason we notice the sour taste of vinegar. We write the equation for a weak acid in an aqueous solution with a double arrow to indicate that the forward and reverse reaction are at equilibrium. Diprotic acids. Some weak acids such as carbonic acid are diprotic acid that have 2H positive which dissociate one at a time. For example, carbonated soft drinks are prepared by dissolving CO2 in water to form carbonic acid H2CO3. A weak acid such as H2CO3 reaches equilibrium between the mostly undissociated H2CO3 molecule and the ions H3O positive and HCO3 negative. Because HCO3 negative is also a weak acid, a second dissociation can take place to produce another hydronium ion and the carbonate ion. Sulfuric acid H2SO4 is also a diprotic acid. However, its first dissociation is complete, which means H2SO4 is a strong acid. The product hydrogen sulfate HSO4 negative can dissociate again but only slightly, which means that the hydrogen sulfate ion is a weak acid. In summary, strong acids such as HI in water dissociates completely to form an aqueous solution of the ions H3 positive and I negative. A weak acid such as HF dissociates only slightly in water to form aqueous solution that consists mostly of HF molecules and a few H3 positive and F minus ions. Strong and weak bases. As strong electrolytes, strong bases dissociate completely in water because the strong bases are ionic compound. They dissociate in water to give an aqueous solution of metal ion and hydroxide ions. The group 1A hydroxides are very soluble in water, which can give high concentration of OH minus ions. A few strong bases are less soluble in water, but what does dissolve? Dissociates completely as ions. For example, when KOH forms a KOH solution, it contains only the ions K positive and OH negative. Strong bases. Some examples of strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So, calcium hydroxide, strontium hydroxide, and barium hydroxide have low solubility as compared to the other acids. Weak bases are weak electrolytes that are poor receptors of hydrogen ions and produce very few ions in solutions. A typical weak base, ammonia, is found in window cleaners. In an aqueous solution, only a few ammonia molecules accept hydrogen ions to form NH4 positive and OH negative. Direction of reaction. There is a relationship between the components in each conjugate acid-base pair. Strong acids have weak conjugate bases that do not rapidly accept H positive. As the strength of the acid decreases, the strength of its conjugate base increases. In any acid-base reaction, there are two acids and two bases. However, one acid is stronger than the other acid and one base is stronger than the other base. By comparing the relative strengths, we can determine the direction of the reaction. For example, the strong acid H2SO4 readily gives up H positive to water. The hydronium ion H3O positive produced is a weak acid than H2SO4. The conjugate base HSO4 is weaker base than water. Let's look at another reaction in which water donates one H positive to carbonate, CO3 2 negative to form HCO3 negative and OH minus. From the table, we can see that HCO3 negative is stronger acid than H2O. We also see that OH minus is a stronger base than CO3 2 negative. To reach equilibrium, the stronger acid and stronger base react in the direction of weaker acid and weaker base. Now we will read about dissociation constant for acid and bases. As we have seen, acids have different strengths depending on how much they dissociate in water. Because the dissociation of strong acids in water is essentially complete, the reaction is not considered to be an equilibrium situation. However, because weak acid in water dissociate only slightly, the ion products reaches equilibrium with the undissociated weak acid molecules. For example, formic acid, the acid found in B, and N-sting is a weak acid. Formic acid is a weak acid that dissociates in water to form hydronium ion H3O positive and formate ion CHO2 negative. Writing dissociation constant. An acid dissociation expression Ka can be written for weak acid that gives the ratio of the concentration of products of the weak acid reactants. As with other dissociation expression, the molar concentration of products is divided by the molar concentration of reactants. Because water is a pure liquid with a constant concentration, it is omitted. The numerical value of the acid dissociation expression is the acid dissociation constant. For example, the acid dissociation expression for the equilibrium equation of formic acid shown above is written Ka equal to H3O positive and CHO2 and divided by HCO2. The numerical value of Ka for formic acid at 25 degrees determined by experiment to be 1.8 into 10 to the power minus 4. Thus, for the weak acid HCHO2, the Ka is written as Ka equals to H3O positive multiplied by CHO2 divided by HCHO2, which gives us 1.4 into 10 to the power minus 4. The Ka for formic acid is small, which confirms that the equilibrium mixture of formic acid in water contains mostly reactants and only small amount of products. Recall that the beakers in the Ka represent the molar concentration of the reactants and products. Weak acids have small Ka value, however strong acids which are essentially 100% dissociated have very large Ka values, but these values are not usually given. The table 14.4 gives Ka and Kb value for selected weak acids. For phosphoric acid, it is 7.5 into 10 to the power minus 3. Nitrous acid 4.5 into 10 to the power minus 4. Hydrofluoric acid 3.5 into 10 to the power minus 4. Formic acid 1.8 into 10 to the 10 to the power minus 4, and so on. And for bases, methylamine, it is 4.4 into 10 to the power minus 4 kb. And carbonate, it is 2.2 into 10 to the power minus 4, and for ammonia it is 1.8 into 10 to the power minus 5. Now let us consider the dissociation of the weak base methylene. CH3NH2 plus H2O gives us CH3NH3 positive plus OH negative. As we did with the acid dissociation expression, the concentration of water is omitted from the base dissociation expression Kb. The base dissociation constant for methylamine is written as Kb gives us CH3NH3 positive into OH negative by CH3 NH2, and its value for Kb is 4.4 into 10 to the power minus 4. Now we will discuss about dissociation of water. In many acid-base reactions, water is amphoteric, which means that it can act either as acid or as a base. In pure water, there is a forward reaction between two water molecules that transfer H positive from one water molecule to the other. One molecule acts as an acid by losing H positive, and the water molecule that gains H positive acts as a base. Every time H positive is transformed between two water molecules, the products are one H3O positive and one OH negative, which react in a reverse direction to reform two water molecules. Thus, equilibrium is reached between the conjugate acid-base pair of waters. Writing the water dissociation expression Kw. Using the equation for water equilibrium, we can write its equilibrium expression that shows the concentration of products divided by the concentration of the reactants. Recall that square bracket around the symbol indicate their concentration in moles per liter. H2O in liquid plus H2O in liquid gives us H2O positive plus OH negative. So K will be H3O positive multiplied by OH negative divided by H2O and H2O. By omitting the constant concentration of pure water, we can write the water expression as Kw equal to H3O positive multiplied by OH negative. Experiment have determined that in pure water, the concentration of H3O positive and OH negative at 25 degrees Celsius are each 1.0 into 10 to the power minus 7 molar. When we place the H3O positive and OH negative ion into the water dissociation expression, we obtain the numerical value of Kw, which is 1.0 into 10 to the power minus 14 at 25 degrees Celsius. As before, the concentration units are omitted in the Kw value. Kw will be H3O positive multiplied by OH negative, and which will give us 1.0 into 10 to the power minus 7 multiplied by 1.0 into 10 to the power minus 7, which will give us 1.0 into 10 to the power minus 14. Neutral, acidic and basic solution. The Kw value applies to any aqueous solution at 25 degrees Celsius because all aqueous solutions contain both H3O positive and OH negative. When the H3O positive and OH negative in a solution are equal, the solution is neutral. However, most solutions are not neutral. They have different concentration of H3O positive and OH negative. If acid is added to water, there is an increase in H3O positive and a decrease in OH negative, which makes an acidic solution. If base is added, OH increases and H3O positive decreases, which gives a basic solution. However, for any aqueous solution, whether it is neutral, acidic or basic, the product H3O positive OH negative is equal to Kw. Using the Kw to calculate H3O positive and OH negative in a solution. If we know the H3O positive of a solution, we can use the Kw to calculate OH. If we know the OH, we can calculate H3O positive simultaneously. From the reaction, Kw equal to H3O positive into OH negative, and if we know the value of any one, we can keep it on the left hand side. Like if we know the value of OH negative, we will keep it on the left hand side, and then we will on the right hand we will put Kw divided by H3O positive. Now we will discuss about the pH scale. In the environment, the acidity or pH of rain, water and soil has significant effects. When rain becomes too acidic, it can dissolve marble statue and accelerate the corrosion of metals. In lakes and ponds, the acidity of water can affect the ability of plants and fish to survive. The acidity of soil around plants affects their growth. If the soil pH is too acidic or too basic, the roots of the plant cannot take up some nutrients. Most plants thrive in soil with a nearly neutral pH, although certain plants such as orchids, camellias and blueberries require a more acidic soil. Personnel working in wood processing, medicine, agriculture, spa and pool maintenance, soap manufacturing and wine making measure the H3O positive and OH minus of solution. Although we have expression H3O positive and OH minus as molar concentration, it is more convenient to describe the acidity of solution using a pH scale. On this scale, a number between 0 to 14 represents the H3O positive concentration for common solution. A neutral solution is the pH of 7, an acidic solution has pH less than 7, a basic solution has pH greater than 7. When we relate acidity and pH, we are using an inverse relationship, which is when our component increases while the other component decreases. When an acid is added to pure water, the H3O positive acidity of the solution increases, but its pH decreases. When a base is added to pure water, it becomes more basic, which means its acidity decreases and pH increases. In the laboratory, the pH meter is commonly used to determine the pH of solution. There are also various indicators and pH papers that turn specific colors when placed in solution of different pH values. The pH is found by comparing the color of the test paper with the color of the solution to a color chart. Calculating the pH of solutions. The pH scale is a logarithmic scale that corresponds to the H3O positive of aqueous solution mathematically. pH is a negative logarithm. pH equals to minus log into H3O positive. Essentially, the negative powers of 10 in the molar concentration are converted to positive numbers. For example, a lemon juice solution which H3O positive 1.0 into 10 to the power minus 2 molar has pH of 2. This can be calculated using the pH equation. The number of decimal places in the pH value is the same as number of significant figures in the H3O positive. The number to the left of the decimal point in the pH value is the power of 10. Because pH is a log scale, the change of 1 pH unit corresponds to 10-fold changes in H3O positive. It is important to note that pH decreases as the H3O positive increases. For example, a solution with a pH of 2 has a H3O positive that is 10 times greater than solution with a pH of 3 and 100 times greater than solution with pH of 4.0. The pH of solution is calculated from the H3O positive by using the log key and changing the sign as shown in sample papers. Now we will discuss about what is pOH. The pOH scale is similar to the pH scale except the pOH is associated with the OH negative of an aqueous solution. pOH equals to minus logarithm of OH negative. Solution with high OH have low pOH value. Solution with low OH have high pOH value. In any aqueous solution, the sum of pH and pOH is equal to 14, which is a negative logarithm of Kw. pH plus pW equal to 14. For example, if the pH of solution is 3.0, the pOH will be calculated as pH plus pOH equal to 14. pOH equal to 14 plus 14 minus pH, which gives us 14 minus 3.5, which will eventually give us 10.5. Calculating H3O positive from pH. If we are given the pH of solution and asked to determine the H3O positive, we need to reverse the calculation of pH. H3O positive is 10 to the power minus pH. For example, if the pH of solution is 3, we can substitute it into this equation. The number of significant figures in H3O positive is equal to the number of decimal places in the pH value. H3O positive is 10 to the power minus pH, which will give us 10 to the power minus 3, which will give us 1 into 10 to the power minus 3. For pH value, they are not whole numbers. The calculation requires the use of the 10 to the power x key, which is usually a second function key. On some calculators, this operation is done using the inverse log equation. Now we shall discuss about the Levi's concept, that is electron pair receptor donor concept, which was started in 1923. G. N. Lewis in 1930 defined an acid as a molecule or an ion that can accept an electron pair from other substance, and a base as a molecule or an ion which can donate an electron pair to some other substance. In other words, a Lewis acid is an electron pair receptor and Lewis base is an electron pair donor. Since Lewis acid is an electron pair receptor, it is also called electron deficient species. Similarly, since Lewis base is an electron pair donor, it is an electron pair rich species. Lewis acid loves to accept the electron pair. It is also called electrophilic, electron philic lover, reagent, or simply electrophile. Similarly, since a Lewis base loves to donate the electron pair to a nucleus, in fact positively charged ions, it is a nucleus lover and hence it is called nucleophile, reagent, or simply nucleophile. Molecules whose central atom has vacant p orbital or incomplete octet of electron in its valence shell, they are the following molecules that act as Lewis bases. For example, BeF2, BX3, here X can be HFCl, etc. In BeF2 molecule, has only 4 electron, complete octet of electron. Similarly, the valence shell of B atom is in BX3 molecule has only 6 electron, so it can readily accept electron and so it can act as a Lewis acid. Molecule whose central metal has vacant d orbital in its valence shell. For example, AlCl3, AlF3, GaCl3, SiX4, GeX4, SnX4, PX3, PF5, SF5. Here you can see like AlCl3, it has vacant d orbitals, and similarly all those compounds which have vacant d orbital, they can act as Lewis acids. Molecules whose central atom is linked with more electronegative atom by double bond, for example CO2, the electronegative and SO2. Simple cations which have low lying empty orbitals. When a simple metal cation Cu positive or Ag positive combines with a ligand, a complex compound is found. In its formation, the ligand donates one or more electron pair to the metal cation, which accommodates them in its valence orbital, and coordinate bond is established. In above reaction, metal cation acts as a Lewis acid and the ligand behaves as Lewis base. This is an example of some Lewis acid Lewis base reactions. Elements which have sextant NS2 NP4 configuration of electron in the valence shell also act as Lewis acids. Variation of Lewis acid strength of simple cation. The strength depends upon following properties. Size of the cation. Smaller is the size of cation, greater is its tendency to accept the electron, and hence stronger is the Lewis acid strength or coordinating ability. Thus, the Lewis acid strength of cation decreases on moving down the group and increases on proceeding from left to right in a period. We know that all trihalides of boron like BF3, BCl3, BBr3 are obtained by sp2 hybridization of B atom in its excited state. Since B atom in its excited state uses only 2s and only 2p, that is 2px and 2py orbital in sp2 hybridization, 2p orbital remains vacant and unused on boron atom. Due to presence of this vacant 2p orbital, the trihalide molecule accepts one electron pair donated by donor molecule and thus form adduct or addition compound with this molecule's ion. Consequently, in this adducts of the trihalide molecule act as Lewis acid and the molecule having the lone pair acts as Lewis base. The measurement of molar heat of formation of the solution of BX3 molecule in nitrobenzene and dipole moment of the adductor NH3BX3 has shown that the Lewis acid character of the given molecule is in the order BF3 greater than BCl3, BF3 less than BCl3 greater than BBr3 and greater than Bi3. This order shows that BBr3 will give more stable adducts than BCl3 and BCl3 will yield more stable adducts than BF3. Now we will read about examples of Lewis bases. Molecules whose central atom has one or more unshared electron pair. Example of such molecules are the hybrids of elements of group Va, NH3, PH3, ASH3, and V and 6, 5A and 6A, H2, H2S and 7A, HF, HCl, Ne, which has 4 lone pair of electron, is also a Lewis base. Almost all negative ions, for example F minus, Cl minus, I minus, OH minus, O2 minus, SO6 minus, etc. Molecule containing C double bond, carbon-carbon double bond. The donation of an electron pair from an pi bond to a Lewis acid like metal ion BF3, AlF3, etc. result in the formation of pi complexes and a number of complex compound of ethylene with Ag, Pt and Rh. The metal atom are bounded not to any single carbon atom but to the pi bond directly. Halides. The halides that can make halide ion available behave as Lewis bases. For example, XCF2, XCF4, XCF6, CSF, NOF, Cu, Cl2, etc. In the following reaction, these halides act as Lewis bases. Relative order of the strength of basic strength of NH3, H2, HF and Ne. We already said that all the substances are Lewis bases. The basic strength of the substance depends on the number of lone pair present in them. Greater is the number of lone pair, lesser is the tendency of the substance to donate the electron pair and hence lesser is its basic strength. Thus, since the number of lone pair in the substance increases as we move from NH3 to Ne, the basic character decreases NH3, then H2, then HF, then Ne. Lux Flood concept. Lux proposed a new concept for acid and bases which was developed by Flood. They proposed a theory to explain an acid-base concept of oxide system. According to the system, a base is any material which gives off oxide ion, and acid is any material which gains oxide ion. A base is an oxide ion donor, and an acid is an oxide ion receptor. Acid plus gives us salt like SiO2 plus CO, CaSiO3, CO2 plus BO, BaCO3, SO3 plus PbO, PbSO4, P2O5 plus 3Na2O, 3Na3, PO4. According to this concept, amphoteric substances are those which have tendency to gain an oxide ion, like ZnO plus O2, Zn2 minus acid, ZnO plus O2 minus, Zn2 positive plus O2 base, Al2O3 plus O2 minus 2AlO2, Al2O3 gives us 2Al3 positive plus 3O2. Advantages. This concept is useful in explaining the reaction which take place at high temperature, example in glass, ceramic industries, metallurgical operation. Limitation. This concept, however, has only a limited scope. So this was all about our Lewis concept and the Lux Flood concept. Now we shall discuss about the solvent system autoionization concept of acid and bases. The concept was introduced by Franklin in 1905 and was extended by Caddy in 1928. The definition of acid and bases given by this concept can be applied for protonic as well as non-protonic solvents. According to this concept, the solvents usually undergo self-ionization and gives rise to cations and anions, which are called solvent cations and solvent anions respectively. The substance which forms solvent cations when dissolved in the solvent are called acids, while the substance which gives solvent anions when dissolved in the solvent are called bases. We can now also conclude that solvent cations can also be called acid cations and solvent anions can also be called base anions. Autoionization of water. Water undergoes self-ionization in the following three ways. H2O gives us H positive plus OH negative, and H positive plus H2O gives us H3O positive. 2H2O H positive plus OH minus, 3H2O 3H2O gives us 2H3O positive plus O2 minus. These three different modes of ionization suggest that according to the solvent system concept, the substance that give H positive or H3O positive ion in water act as acid, while the substance which furnish OH minus or O2 minus in water behaves as base. HCl gives H positive or H3O positive ions in water, hence it behaves as an acid in aqueous solution. Similarly, NaOH, which furnishes OH minus ion, acts as a base. Likewise, for a solvent system of BrF3, the autoionization reaction is 2BrF3 gives us BrF2 positive plus BrF4 negative. Hence, according to solvent system concept, the substance which can give BrF2 positive in BrF3 in acid and the substance which can form BrF4 in base, BrF4 negative is a base. Advantages of solvent system. The definition of acid and bases given by solvent system concept can be used for both protic as well as non-protic solvents. The definition is applicable for aqueous as well as non-aqueous solvents. Limitations of solvent system concept. The definition of acid and bases is based on the nature of solvent, cation and solvent anion obtained by autoionization of the solvent. Acid-base reactions taking place in the absence of a solvent can't be explained, that is acid-base reaction take place only in the presence of solvent. The concept can't account for the acid-base reaction occurring in non-ionizing solvent like C6H6, CHCl3, etc. Now we shall discuss about the HSIB principle, that is hard and soft acid bases theory. Hard and soft acid bases theory is a qualitative concept introduced by Ralph Pearson to explain the stability of metal complexes and the mechanism of the reactions. However, it is possible to quantify this concept based on Klopman's FMO analysis using the interaction between HOMO and LUMO. According to this theory, the Lewis acid and base can be further divided into hard or soft or borderline types. Hard acids, they have small ionic radii, high positive charge, strongly solvated, empty orbital in the valence shell, high energy. And soft bases are large ionic radii having low positive charge, completely filled atomic orbitals, and low energy. Example of strong acid, hard acids are H positive, Li positive, Na positive, K positive, Ba2 positive, Mg2 positive, Ca2 positive. And examples of soft acids are Cu positive, Ag positive, Au positive, Ag positive, Cs positive, Tl positive, Ag2 positive, Pd2 positive. And similarly for HSIB principle, hard bases are small ionic radii having high electronegativity, weakly polarizable and strongly solvated, and they have high energy LUMOs. And soft bases are large ionic radii having intermediate electronegativity, highly polarizable, low energy. Example of hard bases are H2O, OH negative, F negative, Cl negative, PO43 negative, RO, R2O, NH3. And examples of soft bases are RSH, RS, R2S, ICN negative, SCN negative. The borderline Lewis acid and bases have intermediate properties. HSIB principle. According to HSIB principle, hard acids prefer binding to the hard base to give ionic complexes, whereas soft bases prefer binding to soft bases to give covalent complexes. The large electronegativity differences between hard acids and hard bases give rise to strong ionic interaction. The electronegativities of soft acids and soft bases are almost same and hence have less ionic interaction. That is, the interaction between them are more covalent. The interaction between hard acid soft base or soft acid hard base are mostly polar covalent and tend to be more reactive or less stable. The polar covalent compounds readily form either more ionic or more covalent compound if they are allowed to react. Application of HSIB principle. Recovery of Au. The softest metal ion, Au positive gold, is recovered in mining operation by suspending it in a dilute solution of Ca negative, which dissolves the Au. Why is AgI water insoluble but LiL is water soluble? AgI is a soft acid is a soft acid soft base combination, while LiL, lithium iodide, is a hard soft. The interaction between Li positive and I negative ion is not strong in hydrogen bonding. The strong hydrogen bond is possible in cases of H2O, NH3 and HF, since the donor atoms and are hard bases, and the interaction with partially positive charge H, which is a hard acid. Perception reactions. The softer acids like Hg positive, Ag positive, Hg positive, Hg2 positive, etc., and borderline acids like Fe2 positive, Ni2 positive, etc., can be precipitated as sulfides from their aqueous solution, since H2 minus ion is a softer base. Other reactions: formation of stable compounds. Lithium iodide plus CSI gives us LiF, hard, and CSI, soft. AgI2 is a stable, but AgF2 is unstable. Soft Ag positive is a soft acid and 2I negative is a soft base, and that is why AgI2 is stable. Whereas Ag positive is a soft acid, whereas 2F minus is a soft base, and that is why they are unstable. Yes, that was all for our acid and bases reaction. Here we have completed all the types of acid and bases concept like the Arrhenius, Lewis, Bronsted-Lowry, Lux flood, and then we have discussed about the hard and soft bases principle. Thank you all.